All right, so welcome back, everybody. Just a quick reminder, we have our next test. This is test number 2 on Tuesday of next week. So that's going to be held during our lecture. You're going to have the whole time to take it, just like before. Quick reminder about what's on there. You're going to have between 5 and 6 free response questions. They're all going to cover either the Newton's Laws chapter or the applications of Newton's Laws chapter, which we're going to wrap up here today. Okay? There's not a whole lot more to say on this chapter. The last topic is drag forces, and we're not really going to go into a whole lot of depth on this because it's sort of outside of the scope of the class to get into the mathematical details of it. So after this, we'll just go over a bunch of examples. Okay, hopefully that's going to help you as you prepare for the test. So another thing you should be thinking about is, again, going through those review problems and also preparing a cheat sheet that you'll bring to the test on the day of. Okay? So, any questions? All right. Let's get into it then. Drag forces. Does anyone know what a drag force is?
Like air resistance?
Yeah. Air resistance would actually be like an example of a drag force, but it's more general than that. For example, you encounter a whole lot of resistance if you are moving through water, let's say, right? If you swim, you can feel that very easily, right? Or if you like drop a heavy object into water, right? It's not going to just accelerate at 9.8 meters per second squared down because it's experiencing this drag force, okay? So let's get into kind of a more general way of thinking about a drag force. Whenever you have an object that's moving through a fluid, it will experience a drag force that's resisting the motion. It's kind of like friction in a lot of ways because it's a force that opposes motion, but it's not exerted by a flat surface, like in the case of kinetic friction, right? It's instead exerted by an entire body of fluid. So let's take a few examples of this, right? Of course, air resistance is one. If I were to take a piece of paper and drop it, it's experiencing a lot of air resistance as it falls. That's an example of a drag force. But the fluid doesn't have to be air, right? It could be really anything you want. It could be water. Any kind of liquid or gas can exert a drag force on an object that's moving through it, okay? That's the general principle. Now, drag forces are pretty difficult to describe mathematically. Depending on the situation, there are different formulas that may come into play. I'm just going to show you one of them, all right? In this one right here, where is it valid? Basically, if you have a relatively small object moving at a relatively low speed, the drag force is going to be proportional to the speed, okay? And this is just an experimental fact if you just test out different objects moving through different fluids. So if we denote the drag force by D, the drag force is given by some constant B times V, where V is the speed that your object is moving relative to the fluid. So again, this could be your speed moving through the air, speed moving through water, or anything like that. Okay, B, this constant depends on a whole lot of factors. But if you look at the equation, you can see that the larger B is, the bigger the drag force we will experience. So this constant B kind of encapsulates all different factors about the object, how aerodynamic it is, how massive it is, and its shape and things like this, and also properties of the fluid, right? How sort of sticky is the fluid. So we're not going to get into all those details. Suffice it to say, for certain situations, drag force is basically some constant times V. Now, what that's telling us is the faster you move through the fluid, the bigger V is, the bigger the drag force will be, okay? So it's not like friction, where it's just sort of a constant force opposing sliding motion in the kinetic case. Instead, it increases with speed. Okay, that's a pretty key feature of this. So the picture you should have in mind is this. You've got an object moving through the fluid, it's got its velocity going one way, and it's got its drag force opposing that in the other direction. So as far as the direction of the drag force is concerned, it's just like with friction, right? It's opposing the velocity. It's going the opposite direction as the velocity. Okay? So any questions on that so far? Now that takes us to an idea called terminal speed, also known as terminal velocity sometimes, but I think it's actually more correct to say terminal speed. So think about how we've treated free-falling objects up until this point. You know, something you just drop and let it fall through the air. Up until this point, we've been explicitly ignoring any kind of drag force. We've been ignoring air resistance. And under that picture of things, an object is just going to keep accelerating as it falls. The longer it falls, the faster it's going to move. And there's really no limit to how fast it can be moving because it can just, you know, accelerate as long as you want, as long as you drop it from a big enough height, right? So that's not really how things work, right? In the real world, if you drop something, it will reach something called a terminal speed. And again, if I use like the piece of paper as an example, it reaches that terminal speed really quickly. So after an incredibly short amount of time, the paper is no longer speeding up. As it falls, it's pretty much just falling at a constant speed, okay? That's what we want to understand here today. So I want you to imagine you have an object and it's dropped from a very large height. And what I'm going to show you are free body diagrams of that object, okay? Now, what's going on if I just take an object and I drop it? Well, what forces will be present on the free body diagram? You'll have gravity going down. You can be sure about that. But you'll have a drag force going up, which is opposing the motion of the falling body. And the thing about that drag force is the faster the object is falling, the bigger the drag force is going to be, because that's the way it works, right? It's proportional to the speed. So let's draw some free body diagrams of this falling object, starting from the moment when we just drop it, okay? So at the moment I drop something, the moment I release it from my hand, what can we say its initial velocity is? How does that generally work?
Zero.
Be zero, right? So then, right when I drop it, what would the drag force be? Zero. Also zero, right? Because if your velocity is zero, your drag force is also zero, because it's proportional to that, remember? So at the very start of the motion, it's like this. All you've got is gravity going down. You don't have any drag force yet. And so, at least initially, it's just in free fall at 9.8 meters per second squared, as we've discussed before, right? But as soon as it starts moving, right, as soon as it obtains some downward velocity, now there's going to be a drag force, and it's going to be, again, opposing the motion. So this is just a little bit of time later, right? Gravity is always there, but the drag force is now opposing gravity, okay? And so it's not accelerating quite as fast as 9.8 meters per second squared anymore, right? Because there's something opposing gravity, so that's basically going to make it accelerate less than if it were simply just gravity there. And then, as this object continues to fall and speed up, the drag force increases, right? And speeds up some more, the drag force increases some more. Okay, at a certain point, the drag force will have increased so much that it's now equal to your weight, okay? So now your forces are balanced out. Okay, if you move fast enough through the air, the drag force will be equal to the weight in terms of how large that force is. And at that point, what do we say about objects that have balanced forces? In other words, this force cancels out that force. What type of motion are we dealing with?
Constant velocity.
Yeah, now we're dealing with motion at a constant velocity, right? You're not accelerating anymore. We're accelerating as long as there's an unbalanced force acting on the object. But once we get to this situation, where all the forces are balanced, now the object is just falling at a constant velocity, okay? And that's when it's reached terminal speed or terminal velocity, okay? And from that moment on, it's just going to keep falling at that same speed, all right? Has anyone here been skydiving before? No? So the human body, if you skydive, it's going to reach a terminal speed at some point, okay? like I said, drop any object, like a piece of paper through the air, it's going to reach a terminal speed at some point. And that's the effective air resistance. Okay? All right, so I'm going to work something out real quick for you, okay? I want to figure out what the terminal speed of an object is, or some kind of formula for that, all right? So remember, our diagrams look like this at the moment when you reach terminal speed. You've got the drag force going up, and you've got the weight of the object going down, gravity. Okay? And if we do F equals ma on this thing, let's do it in the y direction. Here's what we'll have. So I've got the drag force up minus the weight going down. Okay? And it's looking a little blurry, isn't that? I wonder what's going on with our thing. I'm not sure what's causing that, guys. Sorry. Oh, is that better? Okay. Yeah, so drag force minus the weight equals what? What can I say about the acceleration? Again, once we've reached that terminal speed. Yeah, we're no longer accelerating because we're just, again, moving down at a constant speed. Well, drag force is given by this constant times v. So I'm just going to sub in dv for the drag force. But it's a special value of v, which I'm going to call v sub t for terminal speed. Okay? And then the weight is m times g. That equals 0. So that means the terminal speed is mg divided by b, just like that. All right, so if you have these numbers, you can calculate an object's terminal speed. But I will say, getting this number is not all that straightforward, okay? All right, so that's the result I wanted to show you. So that when terminal speed is reached, we're at v terminal equals mg divided by b. Okay? Is everyone good on that concept? Okay, so this is a much more realistic model of free fall. Okay, so again, I'm just going to reiterate the point. Because of drag forces, falling objects don't just accelerate to the ground indefinitely. They eventually reach, again, that terminal speed. And once that terminal speed is reached, you're no longer accelerating, you just continue moving down at that terminal speed. So now I'm just going to show you some examples of typical values for terminal speeds. We're talking about for an object falling through the air, okay? If it were falling through water or some other fluid, it'd be a completely different scenario, but objects falling through the air. All right, so if you go skydiving, depends on some details, like how massive you are and the shape of your body and what kind of clothes you're wearing, but it's around 150 miles per hour, okay? So you jump out of a plane, that's when you reach terminal speed, about 150 miles per hour. If you were to just drop a baseball off the Sears Tower or something, again, it's not just going to accelerate forever. It's going to reach a terminal speed around 75 miles per hour, right? Raindrops, about 20 miles per hour, okay? They're greatly affected by drag forces, and they reach terminal speed very quickly, which is good, right? If a raindrop actually accelerated all the way from the cloud it came from to the ground, it would do a lot of damage, right? So it reaches a terminal speed. That's good for us. And to a lesser extent, hailstones. These reach terminal speed. Depends on the size. It could be anywhere between like 10 and 100 miles per hour. 100 miles per hour, you don't want to get hit on the head with that. 10 miles per hour, maybe not so bad, right? So again, those are just some examples. And one of the reasons I brought this up is to illustrate a point. What you just saw was an example of a non-constant force, okay? The drag force acting on an object that's falling through the air is something that, as I showed you, increases over time, because the faster it moves, the larger the drag force. And that means we have to treat that kind of problem differently than anything we've seen before. if you think about it, all of the examples you've seen so far, where there's a bunch of different forces acting on an object and you have to apply F equals ma to that object, it's always been with constant forces. For example, pulling something across the floor, we exert a constant force of however many newtons, 250 newtons. What if we allow those forces to change, right? What if we allow the forces to be dynamic and, not just take on the same constant value over time? Well, that's where the calculus comes in, okay? So, again, let's go back to our equation, F equals ma. We add up all the forces, that equals mass times acceleration. A lot of the times what we're doing is we're solving for the acceleration, right? So if the forces are constant, then on the left side of that equation, on the F side, all I have is a bunch of numbers, okay? Sometimes we might write those numbers out as actual numerical values. Other times we'll keep it symbolic, leave them as variables, but the point is they're constants, okay? So in order to solve for the acceleration, we're just doing algebra, basically, right? I'm not saying it's always easy, right? There can be some complicated examples, but what we're fundamentally doing is algebra to solve our system, right? Okay, and that means the solution you get for acceleration is just some number, right? You're going to accelerate at 2.5 meters per second squared or something like that, all right? Okay, here's what it looks like when forces are not constant. You apply F equals ma, and you don't just get an algebraic equation that you can solve using algebra. Instead, you get something called a differential equation. Has anyone heard of this before? You may know it's a course that you're going to take at some point if you're in a certain type of engineering or math major. Is anyone going to take a class called differential equations at some point? Okay. Pretty much all of you, right? Does anyone know what a differential equation is? Does anyone have like a good definition for that? A differential equation involves derivatives, right? So remember derivatives from calculus. It's just an equation that involves derivatives, and in order to solve it, you need to employ some methods of calculus, okay? It's not just algebra anymore. And also, when you solve for the acceleration in a situation like this, you don't just get a number out, okay? The acceleration is not just some constant number. Instead, it's a function of time. It's something that's changing over time, so we can't just give a single value to it. Something like this would be what we get. This is just a random example, but I'm just showing you acceleration as a function of time could be 2.5 times t squared, for example. So we have different accelerations at different times, not just some constant acceleration that stays the same, all right? And we'll do a lot more things like this in Physics 45, but before we move on to the examples, I want to just give you a sense of how this would work, all right? Because I think you've probably taken enough calculus to follow at least the start of this, okay? So here, let's go through that. Let's actually, let's take that same exact example from before. We'll go from scratch. We'll have our drag force acting on our falling object, and then we'll have our force of gravity going down. And what I'm going to do is have the y-axis point downwards, okay? You're always free to set your axes however you like, so it'll just be simpler if we do this for now. Let's do F equals ma. All right, well, it's kind of like what we said before, right? You have these two forces. One of them is the weight. That's going in the positive direction, according to this coordinate system, right? And then the other is the drag force, going in the negative direction, like this, okay? So I'm going to make a few substitutions right in this equation. For the weight, we have m times g. For the drag force, This is given by the constant v times the velocity v. All right? And then for acceleration, on this side we have m times a. Does anyone remember how to sort of define acceleration in terms of a derivative? Acceleration, yeah, go ahead.
Velocity in respect to time?
Yeah, it's so exactly, because acceleration is the rate of change of velocity. And in calculus terms, we can write that as dv dt. So it's a derivative of velocity with respect to time. All right, I'm not going to go all the way into this, but I'm just going to take one more step here. When you have an equation like this, you can separate things out. So I have on this side m times dv, and then I'll divide this whole thing out to put it on the bottom down here. So that's mg minus bv on the bottom there. And then I'm going to take this dt and multiply it through on both sides to put it over here. So guess what you can do? You can integrate both sides of this thing. And what you can do is solve for v as a function of time. Right, so I'm not going to go through that because we haven't all taken integral calculus yet. But I'm just trying to show you that this is an example of applying f equals ma, getting a differential equation out, and then if we solve it, we're finding that because we have these non-constant forces, we have to use calculus to actually do it. Okay? That's just a preview of stuff you'll see in other classes. All right, so just keep that in the back of your head. There's a lot more to this stuff than what we've seen so far. Okay? Okay, so I think that's basically what I wanted to show to you. That takes us to the end of this lecture, but you've got a test coming up. It will be good to see some examples. All right? So let's go through some of those examples. Here, I'll start off with this one. This problem involves a lot of different concepts that are important to know. For one, we're dealing with an inclined plane. We're also dealing with friction, all right? And actually, both are happening at the same time, right? We have, friction while this object is sliding down an inclined plane. So, what does the problem say? A penguin slides down an icy incline on his stomach, as shown in the diagram below. The coefficient of friction between the incline and the penguin's stomach is 0.15. And that's kinetic friction, by the way. The angle of the incline is 25 degrees. That's over here. And the total distance down the incline that the penguin has to go is 25 meters. Let's say the penguin starts off with a running start going 2.5 meters per second at the top of this incline. So gets a running start, 2.5 meters per second, and then just slides down. Okay? Question here is, what is the speed going to be when the penguin reaches the bottom? Okay? So in order to do this, we're going to have to do a few things. Step one, we're going to draw a free body diagram of all the forces acting on the penguin while the penguin is on the incline. Okay? We can use that to set up an F equals ma equation and then solve for the acceleration of the penguin. Right? So then, if we find the acceleration, and we also know the starting velocity, we can find the final velocity, right? How do we do that? If we know the starting velocity, we figure out the acceleration, how do we get the final velocity? Yeah, perfect. So kinematic equations would be how that goes. All right, so there's a lot of different things that come together in this problem. So let's start as a class by thinking of what are those forces that are acting on the penguin while on the incline. Can anyone just name any you can think of? Weight. Of course, the weight, right? Which way does that go?
Straight down.
Straight down, right? All right, what else? There's a normal force. Which way is that going? So it's not going straight up. While the penguin is on the incline, it's going perpendicular to that incline, which is off in this direction. And then what else do we have?
The kinetic friction?
Kinetic friction. Which way does that go?
Going up and
Goes up the ramp, right? And that's it, because we're assuming he's just sliding down the incline on his stomach at that point. So we can use this to solve for the acceleration. Let's do that. So the way I'm going to go through this one, and pretty much all the examples today, is to work symbolically. We're not going to plug in any numbers until the last step. Okay? So here's the incline. And here is the penguin. I'll show it with a little dot. I'll just sketch what you told me. Normal force is going off the incline like this. Kinetic friction is going up the incline like this, because that's opposing the downward motion, right? And then we've got the weight going straight down like this. All right. You may remember that if you're just moving up or down an incline, it's very useful to define your coordinates in this way. We can have the x-axis going down the incline, and then the y-axis coming out of the incline like this. Okay? So, I actually didn't draw that perfectly straight, but the normal force is directly aligned with the y-axis, and the friction force is aligned with the negative x-axis, right? So it's really only the weight, when we use this coordinate system on an inclined plane, that you need to break up into components, okay? So let's show those components. Now, I've seen a trick that some of you do. You sort of like just rotate your whole picture like this. If that helps, feel free to do that. I just tend to do it this way, okay? All right, so next, because I know this is going to come into play later, I'm going to take the components of the weight in the x and the y direction and just sort of figure out what they are. Let's notice that the angle theta of our incline appears up here in the diagram, and then we've got this right angle down here, okay? So we've got WY, WX. How am I going to figure out what WY and WX are?
Sine and cosine.
It's just sines and cosines, right? So you may just know what the answer is because you've seen it so many times in examples, but if not, you can always work it out from scratch, right? This goes for any vector when you break it down into components. Just write down the definition of sine. That's opposite over hypotenuse. What's the opposite side in this case? That's WX. The hypotenuse is like the magnitude of W, so just the overall force, not any particular component. That means WX is the magnitude of W times sine of theta, which is mg sine of theta, right? That's the weight in magnitude is equal to m times g. Okay? So you can probably guess what WY is equal to then. What is it? Yeah, so it'll be when we go through that whole process, mg cosine theta. So I'm not going to go through that because it basically works the same way. Just write down the definition of cosine, and you'll reach this. Okay? So now that we've got all that straight, we can do F equals ma in both the x direction and the y direction. Let's actually start with the y direction, because I can kind of see where this is going. If I use my y equation, I can solve for the normal force, okay? And as we recall, the normal force is part of the equation for the friction force. So we need that just to know what the friction force is. Okay, so how do my forces add together in the y direction?
And minus mg cosine theta.
Yeah, so I'll write it as, I'll just write what's on the diagram, then we'll sub that in. So I'll have n which is in the positive y direction. It's completely aligned with the y-axis. And then minus the y component of the weight, and then that equals what exactly? So basically, what do I put in for the acceleration here? Yeah, I put in 0, because that would imply that we just stay on the ramp, right? Having an acceleration in the y direction would mean I lift off this way somehow. So definitely not acceleration, not accelerating in that direction, right? All right, so the normal force equals the y component of the weight, which, as we said, is mg cos theta. There it is. Okay, does anyone remember how to express the friction force, kinetic friction?
Okay.
Yeah, that's uk times n, but again, n is not just equal to mg, all right? This is a common mistake on the last quiz, actually, is just saying, n is equal to mg. That's not necessarily true, so in general, you have to work it out from scratch. But anyway, we have mu k times n, which is mg cosine of theta, all right? So next, we can see what we can learn by doing F equals ma in the x direction. So again, use your diagram to sort of help you out and use it as reference. Like what forces, just looking at this diagram, are acting in the x direction?
Weight and friction.
Yeah, but in particular, it's just the x component of the weight, just wx. That's going in the positive direction, right? Because it's going down the ramp. Whereas this fk is going to have a negative sign because it's going up the ramp, okay? So again, just look at the diagram to see how to set this up. So I have wx minus f sub k equals max. So of course, I'm not going to set the acceleration in the x direction to 0 because the penguin is definitely accelerating down the ramp, okay? So next, I'm just going to make substitutions. I already know what wx is. I worked that out at the very beginning when we broke down the weight into its x and y components. And I know fk, it's this right here. We just found that. So what do I have? I have mg sine theta minus mu k mg cosine theta equals max. All I'm doing is making substitutions into the F equals ma formula. All right, so ax, I mean, we can just get that by dropping this m factor across the board. See, that cancels here, here, and here. And then on this side of the equation, we have a common factor of g. So I'll pull that out. We have g sine theta minus mu k cosine theta. Okay, at this point, that's something I can plug numbers into. All right? But notice, it wasn't really until that last step where we were able to do that because we had this unknown mass floating around. And if you don't work symbolically, it may be hard to see that it just drops out. Okay? So that's why we work symbolically. So G is 9.8 meters per second squared, right? Okay, what was the angle of the ramp? That's what I'm going to plug in here. We have sine of the angle. What was that again?
25.
25 degrees. Then we have minus mu k, which is 0.15. And then we have cosine of our 25-degree angle. Can someone crunch those numbers and tell me what the acceleration comes out to?
2.8 volts per second squared.
Yeah, so I'm gonna, so of course we have like two sig figs in all our inputs, so we have 2.8, and I'll keep that extra digit of 1, which would be the next digit, meters per second squared, okay? All right, so we did probably the harder part of the problem, because now we have the acceleration, we can use it to calculate the final velocity. Okay, so here's what we know. So now this is becoming like a kinematics problem. We know our acceleration is 2.8 meters per second squared. We also know our initial velocity. That's, remember, v naught x is how we express initial velocity in the x direction in this case. What was that value again?
2.5.
Yeah, that was 2.5. The final velocity, which in our equations we just write as vx, is unknown. That's what we'd like to know. And the distance down the ramp, which you might call delta x because it's just how far you've been displaced in the x direction from the top to the bottom. That's just how long the ramp is. That was 25 meters. Okay? So if you look at these variables, you can probably recall there's a kinematic equation that works pretty well here. I'll just write it down. And someone already mentioned this, but I'm just going to write it down. Vx squared equals v naught x squared plus 2 ax x minus x naught. And that's really what this delta x thing is, right? That's final minus initial position. Okay? So we're trying to solve for that final velocity, vx. If we want to do that, we have to square root on both sides to undo the square, okay? And now we can just plug and chug. We have 2.5 meters per second, square that guy. That's our initial velocity. And then we have 2 times our acceleration. It's 2.8. And we were only able to get that by going through this whole Newton's laws part of the problem, right? And then the distance is 25 meters down the ramp. Can someone crunch those numbers? Yes, about 12 meters per second at the bottom. Okay? So this is a good example of a problem that combines almost everything we've done in the class up until this point, right? It's got kinematic stuff and the Newton's law stuff all in one. Okay? And they do generally get used together. Any questions on this? All right, let's do more examples. All right, this is a good example of a problem with 2 objects that you have to keep track of. Okay, so this problem pertains to this scenario in the diagram. You have 2 masses. You've got M1, which is resting on a table at first. The mass of this guy is 4.5 kilograms. And then you've got M2, which is hanging off of a pulley, which is 5.5 kilograms. Let's suppose that there's friction between this block and the table that it sits on. Coefficients of friction are given there. So static coefficient is 0.54, kinetic coefficient is 0.43. All right. So the question for us is, if we take these blocks and we release them from rest, is the system going to start to move? Right, so imagine I just hold the blocks like this, nothing's moving, and then I just let go. Will they start moving on their own, or will there be enough friction here to just keep everything in place? Okay. The second question that we'd like to address is this. Let's say I set the system in motion. So I don't start off at rest, I just give the blocks a little nudge so they're already in motion with block 1 sliding to the right, and of course that means block 2 is going down. In that case, what will the acceleration of the blocks be? And will they be speeding up or slowing down? All right, a lot going on there, right? So let's work it out. All right, actually, we need that picture for this first part. We're gonna generate free body diagrams, okay? So can anyone tell me what forces are present? Let's start with block 1. What forces are acting on that block?
The table, the natural force.
Yeah, so we got the normal force from the table. That's pushing it straight up. Okay? What else do we have? Tension. There's some tension. There's a string connecting the two blocks. And which way does the tension go if it's acting on block 1? Goes to the right. Remember this about tension. It acts along the length of your string or cable or whatever the connecting thing is, and it's a pulling force. Okay? So we got the normal force, and then we got the tension. What else? Friction. Yeah, that would be opposing the motion like this, right? What else do we have? Weight, right? Yeah, that one's kind of obvious, but we want to say it. So we've got 4 different forces, right? What about over here? What do we have? Acting on block 2. Yeah, there's nothing going on here except weight going down and tension going up. There's not a normal force because it's not resting on any surface. And although, as we learned about today, there's this thing called air resistance, we're going to ignore that, okay? That's always something we're going to neglect. It's a much more complicated problem. All right, so here are the free body diagrams of each block. You need to do them separately because they're separate objects. All right, so let's start with block number 1. That one, as we said, has a normal force going up, a tension force going to the right, some kind of friction force going to the left, and then weight going straight down. Now, both of the blocks have a weight, and it's different for each one. So here's where it becomes important to just label things specifically. I'm going to call this W1, all right? Not to be confused with W2. All right, then we've got block number 2 over here. And its tension force is going straight up. But it's the same amount of tension on either side. Okay? Remember that about, a continuous segment of string? It's the same tension throughout. And we've got the weight going down. Let's draw a coordinate system that we'll use for reference. Let's have x go to the right, y going up like this. All right? I think that'll work pretty well. Okay. So the first question is, if released from rest, will they move? That's the question. All right. So let's start this by assuming they don't move. What can we say about the acceleration of the blocks in that case? Yeah. So if the blocks are not moving, they both have no acceleration in any direction, right? So that means if we do F equals ma for block, let's start with block number 2. Let's do F equals ma on that one. What does that look like? Again, refer back to the diagram. We've got tension going up, the positive y direction. We've got the weight going down. So that would be T minus the weight of block 2 equals 0. That's what would have to be the case, right, if nothing moves. Okay? That means the tension would have to equal the weight of block 2 in order to just hold it there in place, right? and that is m2 times g. Remember, we've got two different masses, you got to label them separately if you want to keep things straight, okay? Let's do block number 1 using this diagram. Okay, well, I can do F equals ma in the x direction. This one's pretty simple, right? We've got tension going to the right in the positive x direction. And we've got friction, and it would be static friction, by the way, if nothing's moving, going the other way. And then again, that would equal 0 because we're just assuming for the time being that nothing's moving. I'll show you where this is all going. Okay, so from this we can conclude that the static friction would have to equal the tension to keep everything from moving, right? To prevent any motion. That's telling us that it would have to equal m2 times g, right? Because that's our tension. I'm just subbing it in. All right, let's do the y direction for block number 1. This is pretty straightforward. The net force in the y direction is m times ay. We have the normal force going up. We have the weight of this block, W1, going down. And that should equal 0, right? Because again, no acceleration. What is that telling us? The normal force is equal to the weight of block 1, which is equal to m1 times g. All that makes sense? You got to just follow the steps, but hopefully each step is pretty straightforward. All right. Let's now remember that static friction is less than or equal to us times m. That has to be the case. This has to hold true if the blocks aren't going to move, okay? If this doesn't hold true, that basically means static friction is not enough to hold the blocks in place, and things are actually going to start moving, okay? So we're just going to just plug some numbers in here to check whether it works, okay? So remember, for static friction, that was m2 times g. That's less than or equal to us times n, which is m1 times g. So the way I'm going to do this is just put the numbers in, all right, on both sides. And actually, we can cancel out g, which will make that even simpler. So basically, m2, what is that? That was 5.5 kilograms. I need that to be less than or equal to us, which is 0.54 times m1, which is 4.5. Does that work? Is it true that 5.5 is less than all this? No, that doesn't work, right? So it's not true what we assumed at the beginning. So this is telling us static friction is not enough to hold the blocks in place if we just sort of let them go, all right? That means they will move if you just let them go from the state that we showed in the diagram. So will they move? Yes, yes they will. Okay, now let's remember there was a second part of this. Now, blocks are moving. Okay, the one on the table is sliding to the right, the other one's going down. The question then is, what is the acceleration of those blocks? Okay, so if in motion, what is the acceleration? That's what we want to find out. All right, so the thing is, the two blocks are connected. And what that means is they can't just have completely separate accelerations, right? The way one of your blocks moves is totally related to the way the other one moves, right? So here, let's just think about that from our diagrams, okay? I'm just going to assume, as a starting point, that for block number 1, we're accelerating to the right. If that's the case, which way would block number 2 have to be accelerating, up or down?
Down.
Yeah. So that's kind of the picture you have in mind, right? Block number 1 is accelerating to the right, which is in the positive x direction, okay? Block number 2 is accelerating down, which is in the negative y direction, okay? So in our equations, if I ever use just the variable a, we're going to let a be the magnitude of the acceleration for both blocks. Because they have to accelerate together. Right? I can't have one accelerating at, 5 meters per second squared and the other at 10 meters per second squared, then they wouldn't be connected. Okay? All right. So here, we're going to go through this process all over again because it's kind of a new problem now. We're going to do F equals ma. We're going to start, how about with, let's do block number 2 as a starting point. Now, remember block number 2, it's accelerating downwards, and there's only forces in the y direction. So I'm just going to concentrate on my y forces. I have the net force in the y direction. That equals MAY. And remember, we're applying this specifically to block 2. So I'm going to have the tension minus W2. That's how I sum up the forces. Okay? So T minus W2. What's that going to equal? My mass, which is M2, times our acceleration. So if A is the magnitude, I have to put a negative sign in there to denote that this block is accelerating downwards, okay? That's where that negative sign is, okay? All right, so I can write that as T equals W2 minus M2 times A, right? I could write it this way just by throwing the W2 to the other side. So that would be M2 times G, that's the weight of the second block, minus M2 times A. All right? So that's pretty much all the info we can get by applying F equals ma to the second block. Let's do it for the first block. So here, now we're going to write down for block number 1 our F equals ma equations. And so some of this is going to be a repeat of what we did before, okay? Let's do F equals ma in the y direction for block number 1. So this is we're looking at the forces acting on block number 1 and only in the y direction to guide us through this equation, all right? What do we have? What forces act in the y direction on block 1? So we've got the normal force going up minus the weight of that block, W1, going down. And what is the acceleration in the y direction for this block?
0.
It's 0. It's only accelerating in the x direction. There's no y acceleration because it's not coming off the table, right? So that means the normal force is the weight of block 1, which is m1 times g. And that's useful because kinetic friction, which is acting on block 1, is going to be mu k times that normal force. So that's going to be mu k m1g. Hopefully you're seeing kind of a pattern for these friction problems. Typically what we do is we look at the y equation to determine a normal force. And then once we have that normal force, we can figure out what the friction force is, okay? That's just what we did here. We all good on that? All right, let's do the x direction. The net force in the x direction equals max. What forces do I have in the x direction acting on block 1 again?
Tension and friction.
Yeah, so I have tension going in the positive direction, and then friction, which is kinetic friction this time, because we're moving, going in the negative direction, okay? So I have T minus F sub K equals, I'm talking about block 1 here, so the mass that I need to use in the equation is M1, okay? What's the acceleration? It's just A, and it's already in the positive direction, so we don't need to add a sign to that, okay? So now we're going to make some substitutions. Fk, that's right here. We have an expression for it already. T, my tension, remember we developed an expression for that over here, okay? So you should already have this on the page. I'm just making those substitutions. This is subbed in for the tension, and this is subbed in for the kinetic friction, okay? So here we go. We have M2G minus M2A, that's our tension. And then for the kinetic friction, we have minus mu K M1G. That equals M1A. So here, in parentheses, that's where I subbed in for the tension, and that's where I subbed in for the friction, okay, just so you can see it. So the rest of this is just some algebra. We need to solve for the acceleration. So the way we should do that is to maybe like collect all the A terms on one side and collect everything else on the other side. So here I have M2 times G, and then minus mu K M1 times G. And then if I take this term, which is minus M2 times A, and I add it to both sides, then I'm going to have M1 plus M2 times A on this side of the equation. Okay, so I'm just shuffling the terms around, right? I'm trying to solve for A, so here it is. A is M2 times G minus mu K M1 times G divided by this, which is M1 plus M2. Now we've just isolated A, and it's an expression in terms of things that we know, which are the masses and the coefficient of friction mu K. So now we can plug in some numbers to this. All right, M2. That's 5.5 kilograms. G is 9.8 meters per second squared. UK is 0.43. M1 is 4.5 kilograms. And G is 9.8 meters per second squared, right there. All right, then we'll divide by the sum of the two masses, M1 plus M2, so that's going to be 4.5 kilograms plus 5.5 kilograms. Can someone crunch those numbers and tell me what it comes out to?
meters per second squared.
Yeah, 3.5 meters per second squared. Okay. So, that's the answer, but let's take a closer look at it just to try to understand what it's saying, what this means. This came out positive, didn't it? if you just look at the formula, it could have easily come out negative if the numbers were different, right? Because I'm taking something minus something else. It just so happened in this problem that the first term was bigger than the second term, so that when you subtract them, you get something positive. It could have been the other way around, right? Where this second term is bigger. What would that be telling us? Does anyone know? If this just came out as a negative number, what would that be telling us?
Blocks are slowing down.
Yeah, that's right. It would tell us that the blocks are slowing down. That is true. And another way of saying that is it would be telling us that the acceleration we assumed was wrong, right? Remember at the beginning, we didn't really know which way the acceleration was going. It could be that this guy is accelerating to the right while this guy's accelerating down. Or it could be the other way. This guy's accelerating to the left, this guy's accelerating up, right? We just assumed it was this way. And because we got a positive number, that means we assumed correctly, all right? If we got a negative number, it just means, oh, everything was flipped around in the other direction compared to what we assumed, all right? That kind of thing happens a lot in physics. There may be a certain direction that you don't know right off the bat, so just kind of choose something, and then if it comes out negative, it just means, oh, it must be the opposite direction that I assumed, okay? All right, so that was kind of a long one. Any questions on this? All right, I want to get to at least one circular motion problem. That's definitely going to come up. You know, we did this one more or less in class. The numbers are slightly different here. But I think we've seen that example. Here's a different example. So we have a space station floating in deep space. And it's shaped like a huge cylinder with a radius of 925 meters. So right away, when I say it's floating in deep space, there isn't any gravity, so to speak. So the reason we experience gravity is because we're standing right on the surface of the Earth. But if we were just really far away from any massive objects, like in between two galaxies or something, there wouldn't be a whole lot of gravity. All right, so assume there's just no gravity. We can actually create something called artificial gravity in this space station just by making the whole space station rotate. Now, if you've seen like any sci-fi movies involving futuristic space stations, you've probably seen this kind of thing before. Can you think of a movie where they do this? They have like a rotating space station to create fake gravity?
I think Interstellar used that.
I'm pretty sure it did. Yeah, Interstellar.
Space Odyssey?
Yeah, 2001: Space Odyssey. That's an old one, but that's probably the first movie that did that. Yeah, so that's actually real physics. Okay. So let's say that the space station is rotating at 1 RPM. That's the frequency that it rotates. So let's imagine that you're a passenger on the space station and you're just sort of standing on the floor here, and the mass is 75 kilograms. What is the normal force that the floor is going to exert on your feet? Okay? So what I'm going to show you is because the space station is rotating in this way, the floor is pushing up on your feet, which creates the sensation of weight, just like as if there were real gravity. Okay? So yeah, let's get to it. Let's figure out what that normal force is. Okay. So it should be pretty clear this is a circular motion problem, right? What are some just general facts we know about circular motion? What can we say about the acceleration of something that's moving in a circle? Yeah, so it's going to be v squared divided by r to give you this acceleration, right? Yeah, that's correct. We're not actually given a value of v, are we? Instead, we're given frequency of rotation in RPM. That's fine. We can vary in a few steps pretty easily take what we have here and figure out what the speed is. In other words, how many meters per second are you moving at? Okay? And once we have that, we can find the acceleration, which is v² over r, and that will tell us something about the normal force. What is the direction of the normal force in this picture here? Yeah, so the floor would be pushing up on your feet like this. That's actually the force that is providing this centripetal acceleration, because the force is going towards the center of the circle, right? That's what we always look for in these sorts of problems. The force is going towards the center of the circle. All right. So the free body diagram is actually very simple. It's like this. There's the rotating space station. You're standing here. And there is a normal force pushing up on you like this. And that's actually all that's happening. Because again, there's no actual gravity here, right? So that's the only force. Now, let's do a little bit of work to figure out how fast you're moving in this circular path, okay? So what we're going to calculate right here is the period. Does anyone remember what the period of rotation means?
1 over frequency.
Sure, that's a way to calculate it, but what does it, mean? What's the definition of period? It's how long it takes for one complete rotation, right? That's what we call capital T. It's 1 divided by the frequency. So frequency is, how many rotations do we make per time? Period is just the inverse of that. So what is our frequency? It's 1 RPM, right? That means we have 1 revolution in every 1 minute, right? So the frequency is revolutions on top, minutes on the bottom, but again, we're flipping that to get the period, okay? Now, I want this period to be in seconds rather than minutes. Basically, the period is 1 minute if you're rotating at 1 RPM, right? But let's convert to seconds. In every 1 minute, we have 60 seconds. So that just means there's 60 seconds for every 1 revolution. Okay? Takes 60 seconds for this space station to rotate 1 time. All right, that's good to know because we can now find the speed. If you're on this space station and you're at a radius of 925 meters, we can figure out the speed you're moving at, right? Speed, v, is just distance divided by time. So in 1 period, the distance you move is a circumference. You go all the way around the circle. So that's 2 pi times your radius divided by the period t. Okay? So it's just important to remember how we go between like frequency and speed. Okay? So now let's put a number to that. We have 2 pi. We have a radius of 925 meters. And then we have a period of 60 seconds. So can someone tell me what the speed ends up being?
Like 969.
Yeah. Sorry, say it again?
0.969. Oh, sorry, I did 9.25 instead of 925.
So it's going to be 96.9,
96.5.
yeah, or 87 if we keep an extra digit, meters per second. Okay. Now let's calculate acceleration. I actually just want to put a number to this. So the acceleration in the radial direction, because remember, if you're moving in a circle, your acceleration goes in towards the center of that circle. That's why I'm labeling it as AR. That's v squared divided by r, isn't it? So now we know both v and r. V is is 96.87 meters per second, and we'll square that whole value, and then we'll divide by 925 meters. Can someone tell me what that works out to?
14 meters per second squared.
You said 10.14? Okay. What is that pretty close to? It's pretty close to G, right? That's where this artificial gravity is coming in. If you just can rotate it at the correct speed, you can simulate the effects of gravity, basically. Okay? And yeah, you can even simulate gravity on other planets where it's much stronger or weaker if you just mess with the speed. Okay? All right, we wanted to find that normal force, so let's do that as our last step. The net force in the radial direction is equal to m times AR. This is just Newton's second law applied to the radial direction, okay? There's only one force acting in the radial direction. That's our normal force. So that normal force is going inwards, so it has a positive sign. Remember, this problem is pretty simple as far as the forces go. There's just one, but just keep in mind that if a force goes in towards the center, that's going to be considered positive, and then if a force is going outwards, away from the center, that's going to be considered negative. So that normal force equals m times AR, which is mv squared over r. We could write it that way if we like. But actually, we already have the acceleration, so we'll just plug the mass times the acceleration in, and then we'll be done with it. Okay, what's our mass? 75 kilograms. What's our acceleration? 10.14 meters per second squared. What's our normal force?
761.
Yep. So 761 newtons, which is, fairly close to the normal force you would feel if you're just standing on Earth, okay? And let's see, I think we do one more. This one's really short. It's another circular motion problem. All right. Has anyone done this before? Gone into a half pipe on a skateboard? Yeah? So, okay. Do you know this feeling? You feel really heavy at the bottom, right? If you start up here, you kind of just drop in. You feel quite heavy, like the skateboard is really pushing on your feet very hard when you're at the bottom. It's not too different from how if you're on a carnival ride. It has like a dip to it. You feel really heavy at the bottom of the dip. Same situation, all right? So the skateboarder has a mass of 65 kilograms. First, let's just find her weight. What is the actual weight of this skateboarder? Then she drops into a semicircular half pipe. The radius of this thing is 2.5 meters. At the lowest point in the half pipe, let's say the speed of this skateboarder is 4.5 meters per second. What is the apparent weight of the skateboarder at that position? So remember, think back, apparent weight, that just means like, how hard is the skateboard pushing up on her feet? We're looking for a normal force, in other words, okay? Because if the skateboarder were actually standing on a scale, it would register something bigger, all right? Let's go through it. So you've got this half pipe. We've got the skateboarder at the very bottom of the half pipe, where we've got what forces are acting on the skateboarder. The weight of the skateboarder, and what else? And then you've got your normal force. And my claim is that the normal force is going to be bigger than the weight. Now, we can do F equals ma in the radial direction. I've got two forces now. One of them is going to be positive, the other is going to be negative. How do we figure this out? For the normal force, what should I assign? A positive or negative sign to that? And what's the reason? Yeah, it's going in towards the center of the circle. Weight will have a negative sign because it's going away from the center. So when we add the forces, we have N minus W equals ma, where the acceleration is v squared divided by r. So it looks like the normal force, which is what we want, equals the weight plus mv squared over r, which is mg plus mv squared over r. So what we're calculating here is how hard is the board pushing up on the skateboarder's feet at this moment, okay? And again, it's going to be not just mg, it's going to be something bigger than that. All right, let's take the mass, which is 65 kilograms, multiplied by g, which is 9.8 meters per second squared, and then v was 4.5 meters per second. We're going to square that value. The radius of the half pipe was 2.5 meters, so that's v squared divided by r, and I just pulled the mass out front. Okay, what's that going to be?
I got 1,163.
Yeah, I'm going to round that off just to about 1,200 newtons. Let's compare that to, so this is what we might call the apparent weight. Okay, the actual weight, the actual force of gravity, not what it feels like, but the actual force of gravity is m times g. And let's just crunch that real quick. That would just be 65 kilograms times 9.8 meters per second squared. What's that equal to?
637.
Yeah, so let's round that to nice 640. So your apparent weight is like double almost your actual weight, the actual force of gravity. So that's where that sensation comes from, like just feeling heavier when you go down into this dip. All right, that's all for today. Next time we're in here, we're gonna have our test.